right, welcome back everyone. I'd like to welcome Juilee, Bhosale, senior data scientist, also at Zillow Group, presenting A/B testing using propensity score matching.
Thank you. Like you said, I'll be talking about A/B testing using propensity score matching. Clearly, it's the technical talk you want to listen to when it posts come up. So hopefully you have your coffees with you. I'll try not to put you to sleep. Basically, for those of you who are in the field of causal inference, you might have heard about A/B testing a lot, and a lot of times what we use is randomized control trials. But a lot of times, randomized control trials might not be feasible, not be ethical, and so what do you do when randomized control trials are not possible? That is where propensity score matching comes in, and that's what we'll be walking through today. What is propensity score matching, how do we do it, and also a real-world example. So before I move into what is propensity score matching, just a quick look at the agenda, what we'll be covering today. For those of you who are pretty new to the field of causal inference, we'll be walking through A/B testing basics, what is a randomized control trial and some of its limitations, and then finally we'll be going to propensity score matching, and then we'll look at a real-world example. So A/B testing, right? Most of you might have heard about A/B testing, but as the name suggests, it's really a statistical comparison test between two or more groups. The idea is we use A/B tests to assess causal impact by applying effect to a particular group known as a treatment group, and by withholding the effect from another group which is known as the control group. So the only difference between these two groups is the presence or absence of a treatment. So naturally, any differences that you see in these two groups can be attributed back to the treatment, and that's essentially the main principle behind the causal inference. But it's not as simple as just comparing test and control groups. You cannot just, randomly take two groups and compare them. One of the basic fundamental principles behind a good experimental setup is you need to make sure that your test and control groups are exactly similar. What that means is basically the only difference between test and control groups needs to be the presence or absence of treatment. So for example, suppose you are running a marketing campaign and you want to assess the impact of this marketing campaign. So you send out a marketing campaign to a group of people to make them purchase bread. And this audience that you're sending out your marketing campaign to are a group of bread lovers. And you do not send out the marketing campaign, so your control group is basically a group of gluten allergic people, because why would gluten allergic people buy bread? But the amount of sales that you see from these two groups are going to be different, and naturally the people who are bread lovers are going to have a higher amount of sales. So does that mean that your marketing campaign was effective? Your email was actually driving the sales? That's not true, right? Mostly the sales will increase because the inherent populations that we are comparing are not similar. So that's one of the fundamental principles that we need to adhere by to make sure that the treatment or the outcome we can completely attribute to the treatment. We want to make sure that the treatment and control groups are exactly similar. And randomized control trials are one of the gold standards for testing. As the name suggests, basically you take a test population and you divide that randomly into a treatment group and a control group. Basically you apply the treatment to one set of people and you do not apply it to another set of people. And because we have randomly assigned them, there are no biases initially in these two different groups, so they are statistically similar. But not always can you do randomized control testing. For example, especially in the medical field, right? Like if you're, say, trying to study the impact of smoking on the risk of heart failure, it would be unethical to sort of, induce one group to smoke and get a heart attack. So in that case, what you could really do is look at a group of smokers and their risk of heart failure and compare that to a group of similar non-smokers. as well as, sometimes you have logistical constraints. And the last one, that's my favorite because that happens to me a lot. Sometimes your stakeholders are just, send the marketing campaign live and without a control group, and they just want you to assess the impact of the marketing campaign. What do you do if you don't have a control? So that's where propensity score matching really comes in. The main gist behind propensity score matching is it's a statistical technique which allows you to artificially create control groups by matching every unit in the treatment group to a similar unit in a control group based on its observable characteristics. And how do we do that? So as the name suggests, essentially what we do is we calculate a propensity score or the probability of a unit being in the treatment group based on its observable characteristics, or something we call as covariates. And we match every unit in a treatment group with a similar unit in the non-treatment group. So essentially, mathematically we express the propensity score. It's simply a function of the covariates. So what that means is each unit which has, or two units who have similar propensity scores are also going to have a similar distribution of covariates. Essentially what that means is both of these units are similar to each other in all of its characteristics except having having whether one is in a treatment group or not. So that basically mimics randomization. So I know that is a lot of words. Let's actually walk logistically through how do we do that. And then we'll also talk about an example of actually how propensity score works. So there are 4 key steps in propensity score matching. The first one is you want to identify your test population and all of the covariates which can affect the outcome. For example, when you take the example of the marketing email, we know that the amount of how much people like bread can affect bread sales. So that's one of the variables that we need to balance or control. So that's our covariate. Then the next step is based on the covariates that we have identified, we build the propensity score. Again, like I mentioned, propensity score is simply a mathematical equation which looks at the probability of a unit being present in the treatment group. So mathematically you express that as a weighted score which calculates the probability of being in the treatment group, right? And the next step is, the last final step is basically you match a unit in a treatment group with a unit in a control group. There are different methods that we can use for this matching algorithm. There is exact matching, you can use nearest distant matching as well as constant exact matching. Essentially what you want to do is for every unit in your treatment group, you want to find a similar unit which has the same distribution of covariates. And last is, after you've formed your control and treatment groups, you want to actually check if they are statistically similar. What that means is you want to look at all of the covariates and actually see if the difference between them is 0. If not, you go back to step 3 and you do a better matching algorithm. We'll actually take a real example of how that would happen in real life. Okay, I forgot this. It was supposed to be a slide and there was some animation. Okay, so you see all the information but act surprised when I'm talking about it. Okay, so step 1 is you identify your control and treatment group. Okay, before that I should explain about the experiment setup. So suppose we take that example of trying to understand the risk of heart failure and the impact of smoking on heart failures. So what you want to do is you want to have a group of smokers and look at their risk of heart failure, but you cannot really run a random trial at the start, right? So what you can do is you can look at a group of smokers and you can compare that to a similar group of non-smokers, and you can just understand the heart attacks or the risk of heart failures in both of these groups. Now what you want to do is you want to understand what are the different covariates which could potentially affect the risk of heart failure apart from smoking, and if you want to control on that. For example, a person who is 52 years old, a 52-year-old female will have a different risk of heart failure than a 60-year-old male. So we want to compare a 50-year-old female smoker to a 50-year-old female non-smoker, correct? So that's what we're trying to find. We're trying to find a 50-year-old female and a similar 50-year-old female in the non-smoker group. So age and gender are the two covariates that we want to balance in our treatment and control group. The next step is we build the propensity score. So we've identified age and gender are the two things that we want to balance. And the propensity score is simply a logistic regression or a log odds equation based on the different covariates. So here our dependent variable is the presence or absence of treatment. Your treatment is basically, is a person smoker or non-smoker. So basically we calculate the likelihood of a person being a smoker given their gender and their age, right? And once we have that propensity score, the final step really is you see this mathematical equation that's calculated, which gives you a probability. And then finally we look at we basically match these two different groups based on their propensity scores. So if you see a female who's 52 years old will have the same propensity score as a female who's 52 years old, but who is a non-smoker. So we basically get two groups which are equally distributed in age and gender. These are the two covariates that we chose. But the only difference between them is one is actually a smoker, or another is not a smoker. And any difference that we see in heart risk from these two groups can be exactly attributed to the fact, to basically the impact of smoking between these two groups. Correct? Next, we'll also talk about a real-world example, basically a real experiment that we did at Zillow. So this was, I know we're short on time, so I'm just quickly going to breeze through this. So this was an experiment where this was an acquisition campaign that we ran for some of our customers. Again, so the setup was we sent out an email to one set of people and we had a similar control group set up for this set of people. However, out of the people that we sent out an email, we selected a group of well performers for a second touch point. And essentially the team wanted to understand what is the incremental value add by this second touch point, or we'll call this a sales call in this example. So because this was a subset of people which were well performers, I could not compare that to the actual original control, just because this is an inherently different population. And because they're well performers and we are looking at whether people are converting or not, their performance could actually affect the conversion rate, and essentially I would be looking at a biased outcome. So again, I used propensity score matching to find out that subset of people from this control group. Essentially we identified, again, I've masked some of these variables, but if you look at the first variable, you can see there is a vast difference between the control and treatment. What that means is inherently these two were different populations. I could not use a direct comparison. So what I needed to do was find out a subset from that control group where the distribution of all of these variables was similar to that subset of well performers that I found from the email campaign. And after propensity score, these are the results that you see. Basically, we follow the same steps. We build out that logistic regression, and then we match all of the treatment units, two similar units in the control group. If you look at on the right side, we had close to like 9,000 potential control group, and we had a treatment group of 548, and at the end we matched 548 of those people to similar 548 people, and those are the results that you see on the chart on the right. Initially, the distribution of variables was completely different, but after the matching we see it's almost similar. That means that both of these groups are comparable, and we can actually compare them and attribute any differences back to the treatment. This is just an example of some of the means that we see. So initially, if you look at this variable 1, 2, they had like completely different means between treatment and control, but in the end we see the means of both of these groups. Both of these groups are similar as well. So that basically confirms that our matched groups that we get are similar in distribution on all of the variables that we wanted to control. And last but not the least, again, propensity score matching is a very powerful algorithm, but like any algorithm, it has its own limitations. The number one being ignorability bias or hidden covariate bias. What that means is it works under the assumption that all of the covariates that we're trying to balance are the covariates that will affect the outcome. For example, in the smoking case study, right, we controlled for age and gender, but it could be that heart failure was actually dependent on dietary choices, and we did not have data about dietary choices. So because we don't include dietary choices, our results could be biased, and all of the differences that we see could not be attributed back to smoking. So essentially, we want to make sure that all of the covariates that we are balancing are all of the covariates that affect the outcome, and we're not missing out on any. And last is, again, propensity score algorithm, like any modeling algorithm, is really dependent on the kind of data that you use, so garbage in, garbage out. If the characteristics that you have are not, we don't have enough sample size, or if they are not good characteristics, that they do not completely explain the outcome that we're trying to measure, we're obviously not going to get good results. So just next time you're trying to, next time you're stuck with your randomized control trial and you don't know if you could use anything else, hopefully you'll remember propensity score matching, and again, I'll be happy to answer any other questions if anybody has.
Thank you for going through this. So one question I have about the read example you had from Zillow. So your treatment group and your control group, the overall one and synthetic one, does not match on these characteristics. What does it say about the general biasability of the results you're getting from the comparison of treatment with synthetic control? Because they're, like in this case, they're not reflective of your overall population, because your overall population has different distribution of these variables.
So let me understand it right. Yes, the treatment and control group are not reflecting of the overall population, but here the idea was we wanted to understand like the impact of the incremental value that this particular second touch point or this event was having. So essentially, we needed a control group as a baseline, and any differences between the outcomes of the treatment control group could be attributed back to. So even if it was not represented with the population, the reason why we were doing this experiment really was to get that incremental lift.
Okay.
Thank you for the great talk. Do you always match one-on-one with the treatment and the control group, or does it make sense in certain cases you match the one treatment to 3 control, for samples?
It depends on your use case. Usually when we're trying to ascertain the impact of a treatment, we basically want to control as a baseline. So it's okay if you have just one control that is one-on-one matching. But it really depends on like your use case of like what you're trying to do. And usually propensity score matching is used when a treatment has already occurred and you want to like artificially create a control group. So one-on-one really makes sense. But again, if there are instances where you need like more than 2 groups, obviously more than one-on-one match can also be done.
Do you want to go through that already asked?
Oh, that's true too.
Sorry, I'm sorry.
You guys are speaking, you're getting your stuff.
Well, I'm back and forth.
I don't know if I can answer this question. Sorry. If I can ask this question, that will make sense, but I guess I see a situation where, like, for example, it's a marketplace and it's kind of hard, maybe hard to determine what is the treatment versus what is the effect. Like, if we bring it back to Zillow example, is that the age who's doing well Or is it maybe like the treatment is placing the agent in this market that is highly convertible, you know, like, so how do we even think about this when it's like, it's not like a clinical trial where we give a pill to a patient, or it's not a baseball game where like, oh, it's individual performance. It's like, it's marketplace, and I'm confused. I'm new to this. So just maybe a few words, how you think
Yeah, no,
about this?
absolutely. I think that's the most tricky part, right? Going back to your example, for example, you know, if it really depends on what is the outcome that you're trying to measure. For example, if you know, it's a question of you're placing an agent in a market that's really good, and you're trying to measure the number of connections that the agent is getting. So all of the things that you would want to control for would be things which affect that number of connections. So if being present in a good market is something that affects an agent's ability to get connections, then that's the thing that you would control. Essentially what that means is you want to compare that agent in a comparable market because that affects his ability to get the connection. So essentially, the short answer is whatever outcome you're measuring, you want to make sure what are the things that affect that outcome, and you want to control for that. And the only thing that you don't want to include in that balancing is the treatment that you're trying to measure. Does that make sense?
Yeah, I guess just quick follow-up, if there is no treatment and I'm just trying to understand like what's going on, what's driving the success, right? Like there's no email, it's just, is this a type of a framework I would think about?
I would say in that event, like A/B testing is especially useful when you have a particular treatment that you're trying to measure, even like causal inference for that matter. But I think for your kind of a setup, I think other techniques like probably regression would be like more influential in understanding drivers.
Just really quick, because there was a causal inference talk and they were saying, well, correlation is not causation. Obviously, I didn't say, you know, those are related. Maybe we can chat later about this, but
Absolutely.
I feel like it's kind of like riding around the circles.
Yeah.
Like,
And also it could be like, you know, if you are trying to assess different fields, you measure one thing at a time. So if like there are 4 things that you think are drivers, you like keep one thing, everything constant, just change one thing, and then you understand like what is the real driver. Okay.
Is propensity, two quick questions, is propensity scoring only for binary treatments? And second, have you seen cases where propensity score matching does not work?
I'll answer your first question. It doesn't need to be binary. Basically, having a treatment is your, one outcome, and not having a treatment is your second outcome. So if you have a treatment, it automatically transforms into a binary outcome. What that means is, you take that smoking example, right? You just look at the group of people who are smokers and group of people who are not smokers. So smoking and not smoking is like the binary. So being in a treatment group and not being in a treatment group, that's always is going to be the dependent variable.
Because what if they're different, so you just one example, what if you want to test different levels of smoking?
Correct, that's okay. Even if you want to test different levels of smoking, the variable is basically, are you in that group where like you're trying to test those different levels of smoking? For example, there's a group of people who are smoking at different levels, and that's your treatment group. And so that's your, one, whatever you assign. And the people who don't do that is 0. And if there are like multiple groups, you can create a control group for each of those groups.